Hello, this is a answer to a question coming from Yulia. The question is about injective, surjective, and bijective functions. Um, I'm not giving any specific problems here. That is, the question didn't ask for anything specific. You can see this is corresponding to some question. So there are some functions which are given somehow by someone. And there's some options, right? Whether the function is injective or surjective, bijective, which would mean both, or maybe it's neither injective nor surjective. And then there's a follow-up question, which is really what we want to answer here is, will the answer depend on the relation, right, or relationship between the domain and the codomain of the function? And then besides that, or maybe instead of just looking at the domain and codomain, perhaps you also have to look at the function as well. And Yulia goes on to ask even more, how do you build some intuition for whether or not a function will be injective, surjective, or bijective? Now, any answer I give here will necessarily be incomplete. There's just way too much to be said, but let me try to give a few ideas. So first, let's back up here to asking, okay, does the answer depend just on this relationship between the domain and the codomain? So why don't we give a couple quick examples to show that it is going to potentially depend on those relationships, but then we're going to see it actually depends on quite a bit more. So here's an example. Let's say I have a set A, and it's just going to have two elements in it. Let's say the numbers 1 and the number 2. And then I'm going to have a set B, and this will have simply an element which we'll call x. Now, if I define some function from A to B, then the only possible outputs, right, for any of the elements in A is going to be this element x, which immediately tells you, right, without having to really do too much, that both 1, in fact, let me draw this sort of diagonally, 1 and 2 are going to be mapped by f to the same value, right, which is x. So you see these arrows collide at x, and this gets back to the definition of injectivity, right? So a function is injective if it has no collisions. Okay, so a collision, right? So I actually use this as a well-defined terms, right? So if my function, so maybe we just call it f, right? Like we have over there. What does a collision look like? A collision looks like f of x equals f of y, where x is not equal to y. Right, so you have two different values which are mapped to the same value by the function. That's a collision. Injectivity is going to say that you can't have such things. So one thing you should be able to see pretty quickly is if you have a set A whose cardinality, that is the number of elements in the set, is bigger than the cardinality of the codomain, then you just won't be able to have an injective function. Right? So if again, I'll have some function g from C to D, and if I know the cardinality of C is greater than the cardinality of D, then immediately this is going to imply G is not injective. All right, and we're going to assume here, right, everything we're talking about finite cardinality. Now, there are instances where we're going to have finite cardinality. However, if you're talking about your codomain or your domain being something like the real numbers or the rational numbers, then you really don't want to rely on such a statement since, well, those are not finite sets. There we might need to say a little bit more. Surjectivity, we can also say something similar. So let's just take these two sets and turn it around. So I'll have a function h, which goes from B back to A. So there's only one element in B, right? That's X. So as soon as I know where it goes, that's it. That's the whole function. So it's either going to go to 1 or 2, right? I'm not sure which one, right? But we could say it's either 1 or 2, right? And the key here is this word either, right? It's not both, right? It's a function. One of the basic properties of a function, the basic property of a function, right, is that you have one input, right, and it's going to go to one output. You're right. It can't split, right? You can't have it. Well, imagine this picture backward. You can't have x going to both 1 and to 2. Okay, so what that tells us is that there's going to be one of these elements from A which is missed, right? It's not covered, we would say, by an element in B. And this tells us that the function h is not surjective, because what does surjective mean, right? So a function is surjective if every element in the codomain is covered. All right, so what does covered mean, right? So if you have, say, f of x equals z, then z is covered, we can spell that, covered by x. All right, so we need every element in the codomain to be covered by something. If you have fewer elements in the codomain than in the domain, or excuse me, I should say more elements in the codomain than the domain, then there's not enough elements in the domain to cover everything in the codomain. So we can make this extra statement. So, right, if you have some function, okay, now we'll call it, say, k, from some set E to a set F, and if you know that the cardinality of F is greater than the cardinality of E, this will imply G is not surjective. Okay, so note that in both of these cases, based on the cardinality, we were able to conclude when something was not injective or not surjective. We will not ever be able to conclude injectivity or surjectivity based on the sizes. Okay, maybe there's one case, right? Like if you're talking about a singleton set, right? One element going to something with one element. But essentially, right, you're not going to be able to ever conclude you have injectivity or surjectivity based on the cardinality. You can only conclude that you do not have them. All right. Cool. So that's sort of, at least when you're just talking about basic sets, that's going to be the limit to what we can do just by looking at the domain and the codomain. If we go to more complicated algebraic structures, such as groups or vector spaces, right? So when you're in linear algebra, you might be able to say a little bit more, all right, based on things like the dimension of the vector space. You'll be able to say something that is very similar to this. Instead of looking at the cardinality, which in those cases will often be infinite, you can look at the dimension of the vector spaces. And again, if, for example, the codomain has a larger dimension than the domain, then, this is supposed to be a k, of course, then your linear transformation will not be surjective. And similarly, if the domain has larger dimension than the codomain, then your linear transformation won't be injective. Okay, fine. So what do we do when we're in some infinite set situation and we need to actually look for some sort of pattern, right? Well, again, the answer is it's just going to depend a lot on the situation. If you're given a specific function, then to show that you have something which is injective or surjective, and of course, remember, bijective just means it's both injective and surjective. If you want to do that, there are certain things you can look for. So what for example, is going to break injectivity? Well, if we're talking about real functions, what breaks injectivity? So things like even powers. Those are pretty bad for injectivity, right? Because if you have a function like x squared, then -1 squared is going to be the same thing as 1 squared. So even powers are not so good, but you have to be very careful here, right? For example, if I write down the function from the reals to the reals, which sends an element x to x squared, this is not injective for exactly the reason we set up above. You have a collision. 1 and -1 collide. Okay, but what if I change the domain to just be the non-negative real numbers? Right? Same function, at least it looks like the same function. The rule is the same. It's not actually the same function because the domain is different. Well, this one is injective. So this is what makes it somewhat tricky, right? Is you can look at the same rule and get a function which is either injective or not injective just based on what the domain and the codomain are. So you have to kind of keep all these things, in your mind. Odd powers tend to be better, right? Odd powers are okay, things like x cubed, because now you just don't have this issue, right? So these are usually going to be injective. Right? I mean, x cubed is injective, we know that. But odd powers generally are going to be injective. I mean, you might mix them with things, right? So why am I saying this usually? Well, because maybe we toss some other stuff in there. So this usually is going to be okay if all we have are odd powers. What about things like sine, right? Or cosine, or more generally, periodic functions? Right? So periodic functions, they're really bad. They're really bad for injectivity. All right. So what do you have? You have something like, okay, sine of pi over 2. We know that's the same thing as the sine of, we'll just add 2 pi, right? So 2 pi plus pi over 2. Right? You go to the same point on the unit circle, essentially. So you're going to get the same value for the sine. So sine, these are usually not injective. Okay. However, if again you restrict the domain, right? So if I take the sine function and I take as my domain, say the interval from -pi over 2 to pi over 2, well, now I don't get any duplications, right? So, and this, of course, goes from -1 to 1. So this is injective. Right? So as if I restrict the domain, again, I can get rid of the injectivity problems. So these are sort of things you can be looking for, but you always have to keep in mind what is the domain, what is the codomain. Surjectivity tends to, in one sense, be a little bit harder to spot because you don't get to see necessarily, all of these things are going to break injectivity. Although, again, even powers are not so good, right? So we could say things like, what breaks surjectivity? So even powers are not great because, well, again, take x squared. Because even powers are going to, right, as x goes to -infinity and infinity, they're going to end up going off to positive infinity, right? Or if I put a negative in front, to -infinity. But the important part is they're going to go the same direction. So you generally will miss all the values down below. So there's x squared is never equal to -1 when we're talking about real functions. So if I take f from r to r, where x goes to x squared, this is just not surjective because it doesn't cover any of the negative values. However, if I replace the codomain with the non-negative reals, then this x goes to x squared is a surjective function because I've basically gotten rid of all of the problems. Okay. Um, Again, things like odd powers are usually pretty good. So odd powers like x cubed, right? These are usually going to give you something which is surjective. Again, just talking about polynomials. Why? Because your graphs are usually looking something like this. As x goes to positive infinity, you'll go off to infinity. As x goes to negative infinity, you go off to negative infinity. And by the intermediate value theorem, you'll hit all of the points in between. So you'll cover all of the real numbers. So that's pretty good. I can't quite copy this over. So sine and cosine, right? Those are definitely not surjective, right? At least if we're looking at all of the real numbers as the codomain. But again, if you restrict the codomain to -1 to 1, then it will be surjective. If you take tangent, though, that will be surjective. Why? Because we know it goes up, right? Of course, it's going to go up very often, right? It actually is periodic. So it looks a lot like the x cubed. If you do some of the other trig functions like a secant or a cosecant, those might not be surjective if you shift them up a little bit because they have all these these sort of looks, and so you might be missing some things in the middle. So those are the sort of things you might be looking for. If it's given in a more abstract way, it can be very difficult, all right, to test the injectivity or surjectivity in your mind. Sometimes you just have to break things down. There are little things that you might start playing around with. So I'll let you look at this, but like let's say you have two surjective functions. You can ask, is their composition surjective? And the same thing with injective. Right, so these are questions to play with, and that can actually help you build a little bit of intuition. You might see that you have some function. So, for example, you know that the log function. Okay, you can see it never turns around or anything, right? So it's definitely going to be an injective function, and you know that x cubed. Right? X cubed these are both injective functions. Right? So if you knew, for instance, that the composition of two injective functions was injective, then if somebody gave you ln of x cubed, now you could use a little bit of intuition, right? And say, oh, wait, I actually know x cubed is injective, and I know the natural log is injective, so their composition should be injective. All right. Well, I hope, Yulia, that this answers your question at least a little bit. Without specific problems, I'm not going to be able to answer everything, of course. But hopefully this gives you a little better intuition, and let me know if you want to see some other stuff. All right. Bye bye now.